Some of us, madam, didn't even attend that class.
Okay,
We had network failure.
Huh?
We had network failure.
Okay. Okay, it was recorded, so I'm going to upload it today.
Okay.
I'll just send you a link to my Google Drive so that you access the last week's meeting.
Okay.
But I'm sure there's someone who attended last week's meeting in this forum. Okay, we're just doing a recap on what we discussed last time. Anyone to just remind us of what we talked about last time we met? Can you see the presentation that is uploaded? Are you guys able to see the presentation that has been uploaded? Are you able to see the presentation that has been uploaded? That is my question. Okay, you guys, if you don't respond, there's no way I'm going to move. So please respond so that I get your feedback.
We're able to download, madam. I've seen the downloading log there.
Okay, all right. So you see, when I'm asking questions, you're quiet. But the other time when my internet went down, you're busy discussing. I heard a lot of voices on the recording. But now that I'm asking questions, you don't want to answer. So please answer. Don't want to just hear voices after I'm out if at all the internet will be poor.
Madam, just a question.
Mm-hmm.
And these the same notes that are on the portal?
Yes, they are.
Oh, okay.
They are the same notes.
Okay. No, I was just getting clarity because I was going through the same, so I was comparing the same.
Okay. So after this, we'll go into hypothesis testing of multiple populations. So I've actually made a video already for that. So, and tomorrow during class from 10 to 12, we have a clash with the distance students. So I'm just going to send you the video on hypothesis testing of multiple populations so that you listen to that. Then on Wednesday, we're going to do analysis of variance, and that will be it. Okay, so I hope we're okay. Is there a question? Okay, so last time we talked about confidence intervals of multiple populations. Specifically, we just talked about two populations. Okay, but today we're going to start hypothesis testing. Now, this is not something new. I'm sure some of the questions in the mid assignment made you to study something about hypothesis testing. Okay, so in hypothesis testing, we're just interested in formulating null and alternative hypothesis, and then testing those claims to in order for us to make a proper decision. Okay, so even as we make the decisions, we need to know which test statistic to use in order for us to either reject or fail to reject the null hypothesis. Then at the end of this, you should also be able to distinguish between type 1 and type 2 errors. Okay, so a hypothesis is just a claim about a population parameter. Note here, we use mu. What does mu stand for? Okay, mu is just a population mean, right? So we use the population parameter. That is why we're using mu here. And sometimes we use also the population proportion, the capital P. Okay, so we use population parameters. We test population parameters. So this was a claim that the proportion of adults with cell phones is 0.68. And the other one is a claim that the mean monthly cell phone bill is 42 kwacha. Okay. All right, so the null hypothesis. Okay, so we have two types of hypothesis. We have the null hypothesis and the alternative hypothesis. So the null hypothesis is just the statement on the ground. It is what exists. Okay, so in this example, we're given that the average number of TV sets in Zambian homes is at least 3. So we can represent it numerically. Say H naught is such that mu is greater or equal to 3. So this just means it's at least 3. That means greater or equal to 3. We don't use sample parameters like the sample mean. No, we only use the population parameter, e.g. the population mean. So never use the sample mean or any sample parameter. Okay, so we always try and test the null hypothesis. Remember the notion that you're innocent until proven guilty. So that is the same notion that we use. Something is okay. So the statement that we try and prove, we'll say it is according to the status until we find information stating otherwise. So for null hypothesis, we always use the signs either equal, greater or equal, or less or equal or greater or equal. We don't just use greater than or less than. Okay, but for the alternative hypothesis, we use not equal or just greater or less. So we're saying the null hypothesis is the statement that may or may not be rejected. So if you have any question at any particular point, please, you can feel free to interrupt me. So the alternative
madam, just to take you back a bit on the previous slide.
Okay.
You said you always like this statement that says always contains the equal to, which is the
less or equal and greater or equal.
So you said these we use them on which one? On the null hypothesis?
On the null hypothesis, because we want to relate to what is there on the ground. If I say 50% of the students in BBA 240 always attend the lectures. So what does that mean? I'm saying that my proportion, I'm saying it's 50%. P is equal to 0.5. Okay. So you're always trying to relate to what exists. So what exists, there's some equal sign, that is some equality that is supposed to be there because you are relating to what is on the ground. If I'm saying that, okay, the proportion is usually above 20%, I'm just saying that my P is greater or equal to 0.2. But for the alternative, it will be the opposite. So if in my null hypothesis I put an equal sign, in the alternative I should put not equal. Okay. And if in my null hypothesis I put less than or equal to, in my alternative hypothesis I should put greater than. Okay. And if in my null hypothesis I put a greater or equal to, then in the alternative I should put less than sign. Okay. Okay, so there is an example. Here it just says that you have a claim that the population mean is 50. So that is how you're going to state your null hypothesis. Mu is equal to 50. Okay, so to test this hypothesis, okay, so what is our alternative hypothesis going to be in this case? H naught is such that mu is equal to 50. What is our alternative hypothesis going to be? That's the question. I'm waiting. Okay, someone is typing. The null hypothesis says mean mu is equal to 50. What is the alternative hypothesis going to be? Hey, I'm waiting for an answer and they're saying, can I please explain? Okay, you guys. Okay, maybe let's just wait a bit. Maybe we're going to get an answer. Some people are typing. Okay, mean is equal to 50. Okay, cool. Okay, let's go back to the previous slide. Okay, so the previous slides, just talked about the alternative hypothesis. It is always the opposite of the null hypothesis. Okay, so since we say that, you remember the other example in which we said that the average number of TV sets in Zambian home is at least 3. So that numerically, that is saying that H naught is just H0, like the null hypothesis. So H naught, that is what I'm talking about. H naught is such that mu was greater or equal to 3. That is at least 3. Okay, so that's greater or equal to 3. Now, the alternative hypothesis in this case is the opposite. So we denote H1. So H1 is such that these dots just imply that is such that mu is less than 3. It is the opposite of mu being greater or equal to 3. Okay, so again, our H1, which is the alternative hypothesis, never contains the equal, greater or equal, or less or equal, or greater or equal. It just contains not equal, less than, or greater than. And this is a hypothesis that may or may not be accepted. Okay, so that was on the previous slide. Now the question that I asked was, in the example that we had, we're given that H naught is such that mu is equals to 50. That is, our mean is 50. So our alternative hypothesis here, as Enoch has stated, is going to be H1 is such that mu is not equal to 50. So to test this claim, we're going to get a sample. So suppose that is our sample, and we find that the mean age is 20. So we use the sample statistic to test what we have. So in our sample, we have found that the mean is actually 20. So that means that it is not the same as what was claimed. So we reject the null hypothesis. Okay, so that was just an example, and I think it's still being explained here. Okay, so what was on the ground was that the mean is 50. Okay, but from our sample, we found that it's 50. It's 20. So we then reject the null hypothesis that mu is equal to 50. So when you reject your null hypothesis, you say that you reject your null hypothesis, but then after that you put a conclusion and you explain what that null hypothesis was according to your question. Okay. There's one thing that you're going to use some often in hypothesis testing is the level of significance, which is the alpha. Okay, so our alpha is our key to identifying the rejection region of the sampling distribution. So our alpha can be 0.1, 0.05, 0.01. It all depends on the question that you've been given. Okay, so the first step is obviously identifying your H0 and your H1. Okay, so in this case, given that your level of significance is alpha and H0 is such that mu is greater than or equal to 3, we can see that our alternative hypothesis there is that mu is less than 3. So our alpha, then we have a lower tail test. And this region that is in blue defines our rejection region. Okay, so our star there will be our critical value. So we always have to look for a critical value, and the critical value is just a value that demarcates the rejection region and the acceptance region. You get that value from the table, and it just depends whether you're using a Z table, a T table, or a chi-square table, or even an F table. Okay, so you can identify your critical value from those tables. And if your H0 was in that manner where the mu is less than or equal to 3, then our H1 was going to be greater than 3. That means we have an upper tail. Okay, so we reject H0 in the area greater than the critical value. And if we have a two-tailed test where we're using equal and not equal, we have those two rejection regions. Okay, now in decision making, you can commit 2 errors. The first error is known as type 1 error. And type 1 error is rejecting a true null hypothesis. So if you reject a true null hypothesis, you have committed type 1 error. And the probability of type 1 error is known as alpha. So when you reject a true null hypothesis, that is type 1 error. But when you fail to reject a false null hypothesis, that is type 2 error. Fail to reject a false null hypothesis. Okay, so that is a wrong decision. Okay, so that is type 2 error. And the probability of committing type 2 error is what we refer to as beta. That be the beta. Okay, so suppose you have a true null hypothesis and a false null hypothesis. If you do not reject a true null hypothesis, you have made a correct decision. There's no error. But if you reject a true null hypothesis, then you have committed type 1 error. Okay, so failing to reject a false null hypothesis is what we call type 2 error. But if you reject a false null hypothesis, you have made the right decision and there is no error. Okay, so any questions up to this? Any questions? Okay, so there are no questions at this point. So type 1 and type 2 error. Yes, is that a question? A question? Okay. Type 1 and type 2 error cannot occur at the same time. Okay. So remember, type 1 is rejecting a true null hypothesis. So type 1 can only occur if H naught is true. And remember that type 2 error is just failing to reject a false null hypothesis. Therefore, type 2 error can only occur if H naught is false. If type 1 error, if the probability of type 1 error goes up, then the probability of type 2 error will go down or will reduce. Okay, sometimes the probability of type 1, okay, so given type 2 error as beta and type 1 error as alpha, when type 2 error increases, that means the probability of alpha will reduce. Okay, and if type 2 error increases, type 2 error can also increase when our population standard deviation increases. Okay, then type 2 error can also be increased if or when our sample size is reduced. Any question? Okay, no questions so far? Okay, so we move on. Okay, so now just going to see how we can test our null hypothesis, our null hypothesis. And in hypothesis testing, you can either use the critical value approach or the p-value approach. So in the critical value approach, you convert your sample statistic to either Z or T. Then determine the critical values from the table. And after that, you define your rejection region and then either reject or fail to reject H naught. And I think in most of the solutions that I gave you for the mid-semester assignment, I used the critical value approach, but I was still making the p-value approach as well. So for those that use that approach, I was still accepting it. Now, so our critical value is also can also be identified as the cutoff value. Okay, so in this case, it is that value that distinguishes the rejection and the acceptance region. So in that particular example, our critical value or rejection region will be to our right. Okay. And that is for a two-tailed test. We have the two sides. Okay, so we have different cases for hypothesis testing of the mean. If the standard population standard deviation is known, then we always use the Z. Okay, we always use the Z distribution. Okay, so our test statistics will be the same. And if the population standard deviation is unknown, then our test statistic is the T distribution. But for large samples, we approximate the T with the Z distribution. Okay. Then for small samples, when our population standard deviation is unknown, we use the T distribution. So there's a difference there just on the large samples for unknown T. For large samples, we use the Z. Okay, so those are the steps in hypothesis testing. Specify the population value of interest, formulate the null and alternative hypothesis, and specify the desired level of significance, determine the rejection region, obtain sample evidence and compute test statistics, then reach decision and interpret the results. I'm sure you're able to follow from the solutions that I gave you for the mid. Those are the steps that you're supposed to have. Okay, so we have an example. And the example reads, test the claim that the true mean number of TV sets in Zambian homes is at least 3. Take population standard deviation to be 0.8. So we first specify the value of interest. Here, it's just the mean number of TV sets in a home. So we're saying that the mean number of TV sets in the home is at least 3. So our H naught will read mu is greater or equal to 3. And H1 will read mu is less than 3. So this is a lower tail test. Okay. So we've not been given the level of significance, but if it has not been given, then you use 0.05. Okay. So what we notice here is that we've been given the population standard deviation, therefore we're going to use the Z distribution. Okay, so we use the Z distribution. So at alpha equal to 0.05, and this is a lower tail test, our value Z alpha is just 1.645.
Madam,
Yes.
Yes, just on the previous.
The previous slide.
Like,
yes.
Where it says, suppose that I don't know, alpha is equal to 0.05. Then when we go in this bracket, there is assume. I don't know if this is the, I think the mu. I don't know if it's mu, which is equal to 0.8. Now, why are we facing the alpha in this one here?
So at this level that we have reached, you should be able to distinguish between alpha and what is this 0.08? This is a sigma, right?
Yes.
Yes. What does it denote in statistics?
The total.
The total what? Can others also come in and help? What does the sigma denote in statistics? The sigma. Okay, some people are typing. Okay. Okay, I can see standard deviation. Which standard deviation? We have the sample standard deviation. Okay. Yes. The population standard deviation. Yes. Okay, so our sigma denotes the population standard deviation. Okay. Uh, Felix. So our sigma denotes the population standard deviation. Okay, so what I'm just from saying is that if the alpha, that is the level of significance, is not given, you use 0.05. So even in this case, alpha was not specified. So when it is not given, you use 0.05. That is why we have used it there. So this population standard deviation is equal to 0.8. Helps you to realize that your population standard deviation has been given. And according to our previous slide, if the population standard deviation has been given, what do you use? What test statistic do you use? If the population standard deviation has been given, what test statistic do you use? Anyone? The test statistic, if the population standard deviation has been given? Okay, yes, we use the Z test, or Z distribution. Okay, so that has just helped us that we're going to use the Z distribution in our example. So let's go to our example now. So our alpha is 0.05. Now, you have to take note of whether you're using a two-tailed test or a one-tailed test. Remember, when we're dealing with confidence intervals, what was the critical value for alpha equal to 0.05? What was the Z value for alpha equal to 0.05 when we're talking about confidence intervals? I've posed the question. What was the Z value, the Z alpha over 2, when we're talking about confidence intervals when alpha was 0.05? Okay, people are typing. Looking for the Z value. Okay, so so it was Helen, it wasn't 1.645. It was 1.96 as done as given us. It was 1.96. Okay, but in this case, for alpha equal to 0.05, we're finding a Z value of 1.645. Why is it so? Anyone? Why is it that now we are finding the Z value at alpha equal to 0.05 is 1.645? You guys are saying I should tell you. I've already explained this, so now you should be able to distinguish. Okay, some people are typing. Maybe let's wait. Okay, yeah. Because at this time, we're not dividing alpha by 2. That is very correct. So we're just going to go to our 0.05. When we subtract that from 1, we're going to have you guys remember the way we're finding the probabilities on the table, on the Z table, given alpha. So our alpha in this case is 0.05. So when we subtract that from 1 minus 0.05, we have a 0.95. So you just go straight on your table, on your Z table, and look for the probability at the probability should be 0.95. And you'll find that your Z value will be 1.645. Okay, but if we're dividing this alpha by 2, we're going to have a 0.05 divided by 2. And it would give us a 0.025. And when we subtract that from 1, we would have a 0.975. Then in the normal table, we're going to be looking for the Z values that correspond to 0.975. Okay, but in this case, we are not dividing our alpha by 2. So we are just going to look for that probability, which is 1 minus alpha. And the values that correspond to that on our Z table is 1.645. And I explained last time on how to get this value. So if you're still behind, please consult your friend or get back to me. Okay, so that is our critical value. That is our Z value. So since we have identified our Z value, therefore we're going to reject all values. We're going to reject H naught if our Z value is less than Z alpha, which is a minus 1.645. So we put a minus because we are on the left of 0. Okay. Though our Z value is just 1.645, but since we're on the left, we're going to put a minus. So it's going to be minus 1.645. So this defines our rejection region. Okay, now that we have our rejection region, we now obtain the sample evidence and we compute the test statistic. So we have our Z, our N is 100, our X bar, which is our sample mean, is 2.81. The population standard deviation we're given, which is 0.8. So we just replace in our formula and we find a minus 2.0. Now, we now compare it to our critical value. Does it fall in the rejection region or in the acceptance region? So, since our Z, which is minus 2, is less than minus 1.645, we reject H naught. Okay. Okay, so if we reject H naught, we conclude that there is insufficient evidence. Okay, there is insufficient evidence evidence that the number of TVs is in Zambian homes is at least 3. So when we put a conclusion, we should use the words that were given in the question. Okay, so we're supposed to conclude here as follows. There is therefore insufficient evidence that the mean number of TVs in Zambian homes is at least 3. Okay, so that is where we're going to end with the critical value approach. We're now going to use the p-value approach. So remember, for the p-value approach, if the p-value is less than alpha, you reject H0. So this is a key statement. If it is less than alpha, then H0 must go. Okay. So if p-value is less than alpha, you reject H0. But if it is greater than or equal to alpha, then you fail to reject H0. So for the p-value, you're just going to get the probability of obtaining a test statistic. A test statistic is more extreme than the observed sample mean. Okay, so let's see how we're going to get that using the previous example. So with the p-value, you're just getting the probability. So you're looking for the probability that x bar is less than or equal to 2.84. Remember, this was the sample mean that we given. Okay, so we standardize this. We're going to have 2.8 minus that 3, which is the population mean, divided by the sample, the population standard deviation over root of n, and we get a minus 2, which is the value that we already found. Now we find the probability of obtaining. So you go on your table and look for this probability. You're going to find that it is 0.02. Okay, what is our alpha? Our alpha was 0.05. So this value is less than our alpha, so we reject H0. Okay, our alpha is 0.05, our p-value is less than that, so we reject the null hypothesis. Okay, so before we move to the next example, any questions? Okay, any question? Okay, so we proceed to the next example. In here, we're given a phone industry manager thinks that the customer monthly cell phone bill have increased and now average over 52 kwacha per month. The manager wishes to test this claim. Okay, so there the hypothesis, the null hypothesis is that the average is not over 52 kwacha per month. Okay, so the alternative hypothesis will be the average is greater than 52 kwacha per month. Okay. So that is now an aperture test. So our alpha is 0.1 for this test. So at 0.1, we look for the Z value, which is 1.28. So that defines now our rejection region. We reject H0 if Z is greater than 0.28. Okay, so Alpha was 0.1. Let's just see how we got that. 0.1 when subtracted from 1, 0.9. So our probability, which is closer to 0.9, is just 0.8997. Okay, so we now look for the Z values that correspond to this value, which is 1.28. Okay. Okay, so now we find the Z value, the test statistic. We put in our values and we find the 0.88. Now 0.88 is less than 1.28, so we fail to reject H naught. So we are not going to reject H naught, and we conclude that there is no sufficient evidence that the mean bill is over 52 kwacha. Now we use the p-value approach. So we look for that probability that x is greater than or equal to 53.1, and we find that the probability here is 0.18. Now 0.18, our p-value was 0.1. So remember, we only reject H naught if the p-value is less than our alpha, but in this case it is greater, so we reject H naught. So you just choose one approach to use, either the critical value approach or the p-value approach. Okay, so we have another example. The average cost of a hotel room in Lusaka is said to be 168 kwacha per night. A random sample of
So the madam has bounced. You are currently the only person in this conference.